Okay, good afternoon or good morning, heavy metals in soil. I am going to present the research about heavy metals in soils and edible tissues of Lepidium megeni and health risk assessment in areas influenced by mining activities in the central region of Peru. Heavy metal pollution has spread around the world, disrupting the environment and posing serious health hazard to humans. Soil is the fundamental sustenance of food crops, and it can be greatly disturbed by heavy metals from natural and anthropogenic sources. The contribution of heavy metals to the soils by natural sources comes from the parent material. These heavy metals are released by physical and chemical weathering process. However, the major contribution of heavy metals as to soils comes from mining and metallurgical activity, use of fertilizers and pesticides, irrigation with wastewater, etc. Solubles, heavy metals ions in soil are the main source of heavy metals in plants. These elements can be transferred and accumulate in agricultural crops, such as maca. They can enter the food, for example, yellow and purple maca, enter the food chain and accumulate in the human body, and may have adverse effects on the health of people who consume them. Maca is a millenary Andean product used as traditional food and medicine by the inhabitants of the Andean region of Peru. And it's also in great demand internationally due to its medicinal properties. On the other hand, heavy metals are characterized by their long persistence periods and have many adverse health effects. This can use a variety of negative health effects, for example, arsenic, long-term exposure to arsenic causes cancers, neurological problems, lung disease. Cadmium, exposure to cadmium causes renal dysfunction, bone demineralization, hepatotoxicity, and hypertension. To exposure to lead causes to brain and kidney damage, and negative hematological effects in children, and chronic effects on the nervous system. The objective of the study was to evaluate the concentration of heavy metals in soils and edible tissues of two maca ecotypes collected from 3 districts of the Junín province. In addition, the potential health risk from exposure to heavy metals was evaluated by estimating the estimated daily intake, hazard quotient, hazard index, and cancer risk from consumption of hypocotyledonous maca. The study area corresponds to agricultural plots with cultivation of Lepidium megeni in the central mountain range of Peru in the regions of Junín and Pasco. The maps shows the location of the maca soil and hypocotyl sampling sites in Hondores, Carhuamayo, and Junín districts of the province and Junín. The samples of soils and maca hypocotylis were collected from the same sampling points. The samples of yellow and purple maca were cleaned and washed several times with potable water and rinsed with deionized water. Air dried and then dried in an oven. Similar procedure with the soil samples. Then the dried sample of soils and maca hypocotylis were ground and sieved and placed in airtight plastic containers and stored in desiccators until digestion. Then each simple sample of maca powder and soil samples were digested in a mixture of 10 milliliters of nitric acid and 3 milliliters of hydrochloric acid. After the digestion of the samples, the concentration of heavy metals in the soils samples and 2 ecotypes of maca were analyzed using an atomic absorption spectrophotometer. Heavy metal bioaccumulation, daily intake, non-cancer risk, and cancer risk were calculated according to the equations shown in this table. Indexes such as via concentration factor, estimated daily intake, hazard quotient, hazard index, cancer risk was calculated by these equations. Results and discussions. This figure shows the concentration of arsenic, cadmium, lead, iron, and zinc in soils under maca cultivation. Cadmium and lead in soil samples exceeded the limit allowed by the national and Canadian standard. Arsenic exceeded the limits regulated by the Canadian standard, but did not exceed that are regulated by the Peruvian standard. Iron and zinc were the most abundant in soils, but were below the recommended limits, which would indicate that there was no anthropogenic contamination associated with these chemicals elements. Soil samples from the district of Hondures exhibited the highest concentration of Hondures of arsenic, cadmium, lead, iron, and zinc. Results that could suggest that the soils of this locality would be more enriched with the 5 metals. Accumulation of heavy metals in yellow and purple maca. The mean concentrations of cadmium and lead and purple maca samples and yellow and purple maca samples exceeded the limit regulated by the Food and Agriculture Organization and the World Health Organization. The mean concentration of arsenic, cadmium, lead, and iron and zinc between the 2 ecotypes of maca were statistically identical because of the cultivation of maca are performed in the same plots plots with soils of similar physical and chemical characteristics. The content of the select metals in the ecotypes of maca was statistically different at the three localities, Junín, Carguamayo, and Honduras. This difference could be attributed to the variation in the accumulation capacity of the plants. The two ecotypes of maca accumulate more zinc. More zinc in their epocotyles, which could be attributed to the amount of bioavailable zinc in the soil and its retention and absorption capacity in plant roots. The bioconcentration factor of heavy metals into maca ecotypes and tree localities. Translocation of chemical elements in the soil plant system is the main pathway of human exposure because plants absorb and accumulate metals in their edible and non-edible parts. The bioconcentration factor is an indicator of the ability of movement of chemical elements from the soil to edible parts of the plant. The bioconcentration factor in yellow and purple maca decreased in the order zinc, cadmium, arsenic, lead, and iron. The bioconcentration factor of heavy metal was lower than 1, with relatively higher values observed for zinc due to a higher ability and mobility of zinc in acid soils. Greater accumulation of arsenic and lead in the maca epocotyles were observed in samples from Honduras and Carguamayo districts. Greater accumulation of arsenic and lead in the maca epocotyles in Honduras and Carguamayo. Estimated daily intake of heavy metals in children and adults. This figure shows the estimated daily intake. The estimated daily intake values of contaminated maca were highest for zinc and iron in children and adults. The estimated daily intake of heavy metals was lower than the oral reference dose. All estimated daily intake of heavy metals were less than 1, indicating a low risk to the food chain. Yellow and purple maca have a low risk to the food chain by estimated daily intake. Estimated daily intake of hazardous of heavy metals has been combined with zinc and iron, which are essential nutrients because toxic metals such as cadmium lead, can interact metabolically with essential nodules and affect human health. For example, iron deficiency increases the uptake of cadmium, lead, and aluminum. Lead replaces zinc in heme enzymes, and cadmium replaces zinc in metallothionein. This figure shows the hazard quotient and hazard index for heavy metal in children and adults. The hazard quotient is a non-carcinogenic risk factor that relates the dose of exposure to the toxic elements and the reference dose. The hazard quotient sequence for children and adults was arsenic, cadmium, lead, the hazard quotient sequence for children and adults was arsenic, cadmium, zinc, lead, and iron in children and adults. All hazard quotient values were less than 1. And therefore, heavy metals studied in harmless with minimal health risk to children and adults. Therefore, consumption of maca by local residents is safe. The cumulative hazard exposure or hazard index of heavy metals was less than 1 in children and adults. Maca intake would not have a significant health effect from long-term consumption of maca hypocotyls. Hazard index of children was higher than adults. This figure shows the contribution of heavy metals to the hazard index. Arsenic and cadmium were the most important contaminants with the highest contribution to hazard index in children and adults, with 57% and 25% respectively. The higher estimated daily intake, hazard quotient, and hazard index values for children and adults is due to the difference in digestion rates of food contaminated with heavy metals, body weights, as well as the exposure time. Cancer risk assesses the potential risk associated with exposure to carcinogenic elements such as arsenic, cadmium, or lead throughout lifetime after the exposure. The cancer risk of arsenic and cadmium were higher than those of lead in the maca samples. The cancer risk values of arsenic and cadmium in maca were slightly higher than the safe level in children and adults. A cancer risk less than or equal to 10 to the minus 6 means there is no risk of cancer, but a value greater than 10 to the minus 4 indicates a significant carcinogenic carcinogenic risk for people. In Honduras, for arsenic cancer risk, in the Honduras locality, the cancer risk value for arsenic in children, value for arsenic was higher than the acceptable limit in arsenic in children, while cadmium was slightly higher than the tolerable level. The total cancer risk values were higher in children than in adults. At all three locations, and increased in the order of Carbomayo, Junín, of Carbomayo, Junín, and Honduras. This figure, the total cancer risk, this figure shows the total cancer risks by toxic metals. Arsenic could be the most predominant contaminant with 72 contribution, followed by cadmium with 27 contribution. Arsenic and cadmium would create a cancer risk relatively higher than the acceptable limit compared to lead. For example, there is the probability of occurrence of any type of cancer in a person during his or her lifetime. Conclusion: concentrations of cadmium and lead in soils and hypocotyls of yellow and purple maca exceeded the permissible limit. Tissues of the two ecotypes of maca accumulated metals and increase in the order of arsenic, lead, cadmium, iron, and zinc. The bioconcentration factor in maca hypocotyls varied for each metal studied, with zinc and cadmium showing the highest accumulation, but with values less than 1. Maca hypocotyls were considered safe and no potential health risks was found for children and adults. The cancer risk for arsenic and cadmium was higher than the tolerable limit in children and adults. In the district of Honduras, the cancer risks for arsenic in children was higher than the tolerable limit, and the residents of this locality would be relatively more exposed to the analyzed metals because of higher hazard index and total cancer risks. Thanks.